Okay, so we are going to be getting into chapter 4 today. Um, so don't forget you have vocabulary due. We're going to be talking balancing equations. Active Chemistry 9 is about balancing equations, and that will be due Tuesday. I'm planning a quiz for next Wednesday. I may end up moving it to Friday, but I know a lot of times athletes are out on Friday, so I prefer doing it on Wednesday. So we'll just kind of see where we are when we get to Monday. So several people have come to my office asking about the online homework. And people are finding this hexagonal diagram useful. Let me see if I can get this to reach. Let's do that. Okay. So remember that you have to start your calculation with an amount. And amounts include mass, moles, and volumes. So that's the very first thing you're going to drag over to the side. Okay. Then you have to figure out where you're going. Now, we aren't really using density right now, so we're basically not going to use this side. So if we're using the rest of this, if you're going clockwise, in general, you're dividing. If you're going counterclockwise, in general, you are multiplying. But you can also use your unit analysis to figure it out. Okay, so if you have mass and you want to get to volume, you can't get there directly. We're going to have to go through molar weight to get to moles. And remember that molar weight has units of grams per mole. So this one is not one we start with. It has two different units. We need to start with an amount. Okay, that's a ratio, not an amount. All right. If we are going this way, we are going to divide by the molar weight because that's going to put grams on the bottom. So you cancel. And that will get us to moles. Then we're going to have to go through this capital M. And remember, that is moles per liter. So in the problem, it has a capital M. But when you put your units in the equation going across, it needs to say moles per liter. Okay. And if you drag the capital M over, it's going to divide it into moles and liters. It's not necessarily going to do it the right way. It's going to put moles wherever you drag the capital M to, but you need the moles to be able to cancel. If you end up in liters, and the question asks about milliliters, you have that added step of changing from milliliters or changing from liters to milliliters with the thousand. Okay. So that might be something that helps you. I'm not going to do an example problem today because we've got a lot of stuff that we need to get through, but that might help you a little bit. I have 3 acids written here. Next week in lab, you're going to be working with an acid. So I'm going to say for your quiz next week, these 3 acids, you need to be able to remember the names of those acids. They are on that polyatomic ion sheet. So you have the names there. Simple rule, if there is oxygen, you're going to change 8 to ic. So without the hydrogen in front, what ion is that? Nitrate. So we're going to change 8 to ic. It's going to be nitric. And then we're going to add the word acid because there's a hydrogen up front. So this is nitric acid. This is sulfate. Now this one's a little bit weird because now we go back to using all of sulfur. So instead of sulfic acid, it's sulfuric acid. But we have the ic in there. So nitric acid, sulfuric acid. And if there's no oxygen, we do the same thing. We change ide to ic, but we stick hydro out front. I don't know where we use hydro when there's no oxygen, but we do. So this is hydrochloric acid. Okay. These 3 are the most common acids you use in lab. That's why I want you to know those going into this week so that when you see HCl on a bottle, you know exactly what it is when you go into lab. Okay. I think that kind of covers things. As I said, I did put some practice problems on active chemistry. So where you click for homework, there's also a tab for practice. And if you click on that, you'll see 2 different things. One is the dilution that what I'm going to do right now. One is problems that are more like your homework. And active has 2 kinds. One kind is where you drag and drop the red and blue. And they have a limited number of those. So some of them are just, it asks the question and asks you to type in your number. Okay, so you'll have both of those in there, and they are both set up to draw from pools. So that means that if you are doing it with somebody else, you might get different questions. If you do it again, you should get different questions. It shouldn't give you the same questions every time you look at it. So you should be able to practice as many times as you want. Doesn't affect your grade one way or another, other than practicing generally helps people. All right, questions? All right, so let's look at some dilution problems. All right, so sometimes you'll see this as M1V1 equals M2V2. I've used C and D so we can think in terms of concentrated and dilute and make sure to keep the appropriate things together. Basically, this runs kind of in two different directions. Either you are given a stock solution that's concentrated and you want to know how much of that you need to dilute in order to make a larger volume, or you're told that it's already diluted and you want to know what the concentration of the new things are. Technically, active might ask you for any one of the four things, but usually we're looking for volume of concentrated or molarity of dilute. Okay, so let's try a sample problem here. Okay, what volume of 15 molar nitric acid is required to make 2 liters of 0.45 molar nitric acid? Okay, so one of the problems you're going to end up running into as we get further and further into the math is that we're going to have lots of formulas, lots of ways of solving problems, and you need to be able to recognize from the problem what you should be doing. So we've had some solution problems where you need to figure out grams and you need to kind of go through this chain of molar weight and molarity and those kinds of things. And then we have dilution problems, which use it. So the when we apply this is when either the problem gives us 2 different volumes of one chemical, or it gives us 2 different concentrations of one chemical. So in this case, it's HNO3 in both cases, and it's 2 different concentrations. So that tells us that it's appropriate to use the dilution equation. Okay, so going across MC, that's our concentrated molarity. Which one is that? Got 3 numbers in our problem. Which one is the molarity of the concentrate? The 15. So of the 2 molarities, it's going to be the higher number because it's more concentrated. So we'll have 15.0, and I'm going to write this out as moles per liter. Remind ourselves that that capital M means moles per liter. The next thing I need is the volume of the concentrate. Is that given to me? No, so I'm just going to leave it as BC. Then I need the molarity of the nitric acid diluted. That's this one.
Say M stand.
This capital M is molarity. So that's what I would say out loud if I were reading this, or if I'm. So molarity is the whole concept. Molar is what I would say. So it's 0.45 molar. And molarity is the same thing as moles per liter. And then the 2.00 liters is my volume. All right. So when everything you're doing is multiplying or dividing, it is fine to do it stepwise. It is fine to do it all at once, whichever you're happy with. So sometimes people are like, I just want to stick it in my calculator once. That's fine. But show me this so I know what you're plugging into your calculator. Because if you don't show your work, you don't get credit. And if you're doing step by step, go ahead and write down the answers for each step. And that way, if you make a mistake somewhere along the way, I can give you partial credit. Okay, so I'm going to go ahead and do this step by step. So I'm going to multiply the 0.45 by 2. my calculator gives me this. Is that the correct number of sig figs? No. So if my calculator, which doesn't know how to do sig figs, is chopping off a number, it's because the significant figures are zeros. So I'm just gonna stick in the number that I need. How many do I need? How many total sig figs do I need on that side? Oh, 3 and 1. Let's average that. So this one has only 2. And this one has 3. So we go with the lesser amounts. We need 2 sig figs, but this is not significant. Remember, those leading zeros are not significant. So I'm going to put 9, 0. Okay. Then I'm going to look at my units. I've got liters on bottom, liters on top. Those cancel. And so I'm going to put moles. All right, then going back to algebra, I'm going to say in order to get this guy, which is what I'm looking for by itself, I'm going to have to divide both sides by the same thing, do unto one side as we do unto the other. All right, so my moles per liter cancel and my 15 cancels. Now, sometimes this throws people when I've got my liters that are in a per situation here, but it's on the bottom of a fraction. So let's think back to when we first learned about fractions. One of our rules was about dividing fractions. If you're dividing a fraction, it's the same thing as multiplying by the reciprocal. Remember that from fraction days? So we're going to think about this as being a fraction. It's units, but we can still think of it as a fraction. So instead of dividing by those, I'm going to multiply by the reciprocal. So the reciprocal of moles per liter is liters per mole. Okay, now I can look at those units and cancel them pretty easily because I've got moles on top, moles on bottom, and my liters is on top where I want it to be. Okay. So then I use a calculator because I don't want to try and do that in my head. My calculator tells me 0.06. How many sig figs should I have? 2. Now remember, this isn't significant, but neither is this one. Okay, so we're not looking is it before or after the decimal point. We're looking at is it before or after the non-zero 6. Okay, and so since the 6 is our first sig fig and I need 2, what am I going to do? Add a 0. All right. So I go and I try and find a graduated cylinder that is marked so I can do 0.06 liters, and I can't find one. All I can find are graduated cylinders marked in milliliters. So what do I need to do? To convert, and it's going to involve 1,000, right? Milli means 1,000. So I'm coming from liters. From goes on the bottom. I'm going to milliliters. Milliliters goes on top. And then do I have 1,000 milliliters in a liter or 1,000 liters in a milliliter? 1,000 milliliters, okay? So there's 1,000 miniature marshmallows, which are about 1 milliliter in 1 liter. Okay, so I can plug that into my calculator, or I can remember, oh, this is just moving 3 places. So I'm going to move that decimal 1, 2, 3. So it's 60 milliliters. But that kind of looks like I only have 1 sig fig. How can I show you that I really have 2 sig figs? Just decimal point after the 0. Now, if you have Dr. Hamilton next semester, he kind of likes putting things in scientific notation. I hate looking at scientific notation if I don't have to, but if you want it in scientific notation, you could say 6.0 times 10 to the 1, which is like saying 6 times 10 is 60. But I think that's kind of silly. And that way it's very clear that this 0 is significant because it's after it is. Okay, let's try it in a different direction. Okay. What is the concentration of dilute? What is HCl? Hydrochloric acid. If 125 milliliters of 1.5 molar HCl is diluted to 750 milliliters. All right. So how do I know this is a dilution problem? Well, the word dilute as a verb in there is very helpful. Oh, there it's an adjective, but here it's diluted. That's verb. Okay, so that's a good indicator. But I've also got two different volumes, but I'm only talking about one chemical. So that tells me that I'm taking that chemical and I'm changing its volume. That's a dilution. All right, so MC, that's my first thing. Do I have MC? I have one M. Is this concentrated or is this dilute? So if I'm not sure, let me check the volume. A smaller volume and a larger volume. The concentrated will be the smaller volume. So since it's 125 of this, this is concentrated. This is dilute. So MC is 1.5 molar, 125 milliliters is my VC, my volume of concentrated. And that's equal to, I don't know MD, so I'm just going to leave that as symbolic. And then 750 milliliters. Now I could change this to liters, but since both of these are given in milliliters, I know that they're going to cancel out. Okay, so I'm going to leave those in milliliters rather than switching to liters. And then I only have one M, and that's what I want for my final answer, so it's fine. Okay, so I'm going to multiply one side. I'm just really into the fives today. I get 187.5. Do I get to keep all that? No. So 2 sig figs and 3 sig figs. Now, if I wanted to, I could leave it for now and round at the end. That would be fine. But if you want to make sure all along the way you're keeping the right sig figs, we would say, okay, I need only 2. So this is 1,9. And then what do I do? Do I leave it at 19? Add a 0. So kind of like over here, it was chopping off the 0. Here, I need an extra 0 as well, just to show me how big the number is. Okay, but no decimal point. The decimal point would mean that's significant. This is not significant. I'm going to go ahead and leave both of these. I haven't canceled anything yet, so I'm just going to leave it like that. Then, like a good algebra student, I'm going to do onto one side as I do onto the other. So to get my variable MD by itself, I'm going to divide both sides by this. And this is where the magic happens. Of course, everything over here is going to cancel. But on this side, those milliliters are going to cancel. And now I don't have to worry about having changed it into liters. Okay. So I'm going to have 190 divided by 750. So this is giving me 0.25333. But since I only get 2 sig figs, I round it to 0.25 molar. Now, if I had left it as the 0.1875, I would have gotten exactly 0.25. So it came out to the same answer, whether I rounded it first or not. Sometimes it's a tiny bit off in the last digit. Okay, so questions about that? All right. Now, we're going to go on to chapter 4 and balancing equations. So when we balance an equation, what we're gonna do is try and make sure that we have the same atoms on each side of the equation. And the reason we do this is because of conservation of mass. So if you remember, conservation of mass says the mass of the reactants equals the mass of the products, right? And the reason that happened, according to Dalton, was because the atoms weren't created or destroyed. So when we balance an equation, we're showing that those atoms didn't get created, didn't get destroyed, and they didn't change from one element to the other. Okay, we're not doing nuclear chemistry here, so we're not going to change one element to another. All right, so conservation of matter. This is what I call it when we're talking about the atoms rather than weighing them, but it's basically the same idea as the mass. So ultimately what we want to do is be able to count up the atoms on one side and count them up on the other side, and they should be equal. Now, when I say this, conservation of matter says we should show the same number of atoms on each side of the equation for each element. That means that carbon atoms equal carbon atoms, hydrogen atoms equal hydrogen atoms, but we don't have to have carbon equal hydrogen, right? We don't have to have two of every single element. And I don't think most people confuse that, but like if you've never heard a balancing equation, it kind of sounds like that's what I'm saying. That's not what I'm saying. Okay, we just need all the carbon atoms to be balanced, all the hydrogen atoms to be balanced. Okay, so first we're going to do rules. And we're going to use as an example this simple equation. All right. So, in this equation, this is how we make water. Yesterday, Dr. Fraley came in and he said, you know, we don't have enough deionized water for the labs. We need to make some water. So I could change the filter, or we could, you know, fill a balloon with hydrogen and oxygen and light it on fire, and then we would make water. So that's what we're doing here. I said the air has too much water in it already. We don't need any more humidity. So he went and he put in the filter. But this is how you could make water. And is it balanced right now? No, because we've got two oxygens here and we only have one oxygen over there. So we might think of different ways to balance it. So first are the two rules that you can't do, and then is the rule that you can do. You might say, hey, I see that all I'm missing is an oxygen. So let me try and put an O here. You are not allowed to do that. When I give you an equation, all of the chemicals that are on both sides of the equation are already there. So you don't get to add any chemicals. You don't get to say, what if that chemical weren't there? That would make my life easier. No, you have to work with the chemicals that are given to you. So the first rule is do not add or remove chemicals. So then you might say, well, fine, okay, I won't add any chemicals, but I'm going to put, and let me do this in a different color, a 2 here. Now I've got two oxygens on both sides. Why is that bad? Yeah, this is a different chemical. This is no longer water. Now, sometimes if you do that, it's like a chemical that doesn't exist. This one happens to exist. It's hydrogen peroxide. And if it's too concentrated, that could burn you. It gives very severe, painful burns. So we don't want to mix those two things up. All right, so we stick with the chemicals that Dr. Knapp gave us. We do not change the subscripts. All right, so the subscripts tell us how many atoms in each molecule. All right, so those are the two rules that you can't do. What you are allowed to do is change the coefficients. Okay, ultimately, we want to have whole numbers and we want to have the lowest ratio of them. So we don't want to have like 10, 10, 10, 20. You know, that would be silly. It could be 1, 1, 1, 2, and we have that same ratio. So we want the lowest possible whole numbers we can have. So if I were going to do this equation, I might think about the molecules that are there. Because remember that those coefficients are telling me how many molecules. So I have one pair of little tiny hydrogen atoms, one pair of bigger oxygen atoms, and right now I have one water molecule. But I also have this leftover oxygen. So what I'm going to have to do is make there be two oxygen or two waters. Okay, so now I have two water molecules. So am I balanced? No. My problem is that I've got 1, 2, 3, 4 hydrogens on this side, but only 2 over here. But I can fix that by making there be 2 hydrogen molecules. Okay, so my drawing that is really just to reinforce that when we're changing the coefficients, we're just adding more of the same molecule, because we know when chemical reactions occur, it's never just one molecule. Remember, our moles are these huge numbers, so we always have huge, astronomically large numbers that we're working with. Okay, so we've got plenty of atoms that we can react with. Okay, so